Okay, this is lecture 4 in fact. Now I know that the lecture 3 was not recorded, at least 10 minutes at the end was not recorded. And this is the last thing I did from yesterday. So it's good I didn't erase it. So I will do this problem again for you. I don't know what I was saying about symmetric matrices at the end, but I guess that was what I wanted to say. So let's see. Now we have. Okay, let me. So I was solving this problem. Look at here, lecture 4. And I know what it is, so let me erase it and do it again. So I think it was like this, solving systems of differential. And we start with 2 equations and 2 unknowns. So, and it was something like this. I had x prime or y prime equals a11, a12, a21, a22, x, y. And then I said, okay, if I assume that x, y is like this, v1, v2, e to the power lambda t, which means that x is v1 e to the power lambda t and the y is v2 lambda t. Then plugging these things here, so I have x prime, y prime, so that's the prime of this thing. So I have lambda v1, v2, e to the power lambda t, and this side it is simply a11, a12, a21, a22 times this. Okay. And this is the derivative. So the derivative is lambda e to the power lambda t, and v1, v2 is just, that's a constant. And so if I get rid of the e to the power lambda t, divide by e to the power lambda t, so this and this they cancel out, and I have this thing. Lambda times this vector v is matrix A times v. Or if I write it like this, which we are used to. And I said, okay, this, I ended up with an eigenvalue problem. So to solve this system, we have to find eigenvalues and eigenvectors of A. So to solve the system, we have to find eigenvalues and eigenvectors of A. Okay. So the problem of solving this comes down to finding eigenvalues and eigenvectors of, in this case, 2 by 2, and we will see if I have more than 2, I have n, that is eigenvalues and eigenvectors of my n matrix. So this results in, for 2 by 2, this A, V equals lambda V, remember it results to determinant of A minus lambda I equals 0. This is the characteristic equation, right? and that's a polynomial in lambda. So let me erase everything and just write this thing here. So I am left with E lambda, which is determinant of A minus lambda I to 0. And since it is 2 by 2, that will be a polynomial of degree 2. So this will be polynomial of degree 2, like say A lambda squared plus B lambda plus C equal to 0. It gives me something like this. And this characteristic equation gives me, I have 3 cases here. 2 distinct roots, lambda 1 and lambda 2, 2 complex roots with alpha plus minus beta I, and 1 root with multiplicity 2. Well, let's call it just that. Okay, so these are the 3 cases, and I will discuss the first 2, not the third one. The third one is I don't know where it can happen in practice. Well, it's good to know anyway. Okay, so let's discuss the first case. So, and give you examples of the first case. So the first case is this. So case 1, so we have P lambda, A lambda squared plus B lambda plus C, and case 1, we have lambda 1 not equal to lambda 2, distinct solutions. And lambda 1 gives me V1 eigenvector, and lambda 2 gives me V2 eigenvector. So I have 2 solutions then. X, Y, the first one, let's put 1 here, will be V1, and this is a vector, e to power lambda 1 t, and the second one is lambda 2 v2 e to power lambda 2 t. So xy, in fact, that is the complementary solution, will be c1 times this, a constant times the second one. So it is c1 v1 e to power lambda 1 t plus c2 v2 e to power lambda 2 t. So basically your job is finding eigenvalues and eigenvectors, that's all. The rest is just routine. Just write down the formula and then that's your final solution. But that is in fact that complementary solution. We will see how to solve when we have a forcing function. So that is the case that we have 2 distinct eigenvalues. And that example was in fact the 2 distinct eigenvalues. So let me discuss this. Solve it again. So example will be the one I did yesterday. and it was xy equals x prime y prime, sorry, equals 1, 1, 4, 1, I remember this, x and y. And I said, well, let's take x at 0 to be 1 and y at 0 to be 2. I need initial conditions, so those are initial conditions. That's to find C1 and C2. So let's do it. So A is 1, 1, 4, 1. Determinant of A minus lambda I is this determinant, 1 minus lambda, 1, 4, 1 minus lambda equal to 0. So I have 1 minus lambda squared minus 4 equal to 0. And that gives me 1 minus lambda squared is 4. And 1 minus lambda is plus minus 2. And that gives me 2 lambdas. Lambda 1, negative 1, lambda 2 is 3. Okay. So these are two distinct real eigenvalues. I should have said that first case is in fact two distinct real. In fact, the complex case, they are distinct, but that's complex. So let's find eigenvectors for these two. So those are eigenvalues. Eigenvectors, I should solve this system. 1 minus lambda, 1, 4, 1 minus lambda times V1, V2 is 0, 0. Now this V1, V2 is not that V1, V2, those are vectors, these are just scalars. So you can write anything. I guess the book uses some other notation for that. You can just use anything. So for lambda 1, let me erase this and do each one separately. So lambda 1 is negative 1, and it's I just need one row. Remember I told you, in fact, when you set this to be 0, the determinant of this, you are forcing the two rows to be linearly dependent. So I don't need the second row. So 1 minus, well, let me write it with, so that's 1 minus lambda times V1 plus V2 is 0, right? So this will give me 1 minus lambda, that is 1 plus 1, V1 plus V2 is 0, and that is the 2 V1 plus V2 is 0. Okay, so if I let, which one? So let V1 be 1, then V2 is negative 2. So this gives me the eigenvector. The vector is in fact 1, negative 2. So, yeah, 1, negative 2. Okay, so lambda equals 3. So 1 minus 3 times V1 plus V2 is 0. And that gives me minus 2 V1 plus V2 is 0. And if I let V1 again be 1, then V2 is 2. So this gives me the second eigenvector, and that is 1, 2. So I have the eigenvalues and eigenvectors, and that's it. So I know how to write the general solution, so let's write the general solution. I can do it here. I have space here, so it's general solution x, y. Remember, it was constant 1 times vector 1 e to power lambda 1 t plus constant 2, vector 2, e to power lambda 2. Right? So it will be, keep this down. So that is xy. C1, V1 is just 1 negative 2, e to power minus t, that's minus 1, plus C2, that is 1, 2, e to power 3t. So that's general solution. But I have initial conditions. I set x at 0 to be 1 and y at 0 to be these two. So let's write this. So x is the first row, so let's write x explicitly, not in this form. That is C1 times 1 times this, so e negative t, C1 1 plus C1, C2, e 3t. The second row will be y is minus 2 C1 e negative t plus 2 C2 e 3t. Okay, so x at 0 is 1, y at 0 is 2, and so this one and this one together will give me x at 0 is 1 equals 0 will be 1, 1, so it is C1 plus C2. This one is 2 equals minus 2 C1 plus 2 C2. Okay, so if I multiply this one by, so row 1 times 2 plus row 2, it gives me, if I multiply this by 2, I will get 2, 2 is 4, and do I have 4 on the other side too? So I have 2 equals 2 C1 plus 2 C2, and here I have 2 minus 2 C1 plus 2 C2, and so this is 4 equals 4 C2, and that C2 is 1, and C1 is 0. Is it? I don't like this thing. I want C1 to still exist, so let's choose something else, right? So let's choose 2, 2, right? Yeah. So let's change this, because in this case I'm just getting rid of C1. I don't want to get rid of C1. So there is 2 here, and the same thing. 2, 2 will be 4, and 4, no, it's not 4, this is 6 now, 6 is 4. C2 will be 3 halves, and C1 will be, what's that? C1 will be 1 minus 3 halves, right? No, 2 minus 3 halves, that is 1 half. Let me double check. 2 minus 1. Okay, so I changed that to 2 and 2, so this gave me these solutions. X is C1 1 half e to the power negative t plus 3 halves e to the power 3t, and y is 1/2 times minus 2 is minus e to the power negative t, and 2 times c2 will be 3 plus 3 e to the power 3t. Is it correct? I think it's okay. So let's erase this. Okay. Now I can write this in this format. In fact, C1I, we found C1, C2, and I can leave it like this. But this is the solution, in fact. But what is it? Let's just analyze this thing a little more. So what does this remind you? Go back to maybe Calc 2. What does it remind you? It is x and y are given as functions of time. Well, I said time, but it doesn't have to be time, but most often it's time. So when x and y are given as a function of, say, t, this, remember from Calc 2, we call this parametric equations, right? So these are parametric equations with parameter t. So in fact, we have parametric equations with parameter t. And how did we find these two? Well, while we go back to this, let me make other points here, then I will go back. So if I graph this thing, what do you think I get? Well, I have graphed this thing for you, and I know what you will get. So starting at the t equal to 0, where does it start? At 0.22, right? So if I graph this, let me erase this. Now if you use Wolfram Alpha or Mathematica or something at home to graph it, so if I graph it, so I need parametric plot in Mathematica. So if I parametrically plot this thing, say, if I start at t0, starting at t0 to something. First of all, let me look at this. If I go too far, if t is too large, what happens? In fact, I had to go up to 0.4, from 0 to 0.4. Yeah, I can just continue, but let's look at this and see what this looks like. Now, this looks like this. So you start at 0.22, if this is 2 and this is 2, you start here. And then it will be y over x is, so that's about 2, so this will be something like this. You will see something like this. It's a curve, but a curve with very low curvature and high radius of curvature, and so this is at time 0, say, up to time maybe 0.04 seconds maybe, or hour, or whatever the unit of time is, and the 2 and 2 might be centimeters, might be meters, whatever, kilometers, or. So if I graph this thing, that's what I get. So my solution combined in xy plane as a parametric equations for a curve is this. So this is like parametric equations, remember, parametric equations for a curve. So that gives me a curve in xy plane. Separately, they are just functions of time, so we can graph them. I didn't graph it, I don't know, but it should be something like e to the power 3t, in fact, because the e to the power minus t doesn't come into the picture. So it should be, both of them should look like this. So at time 0, if this is say time and this is say x, for example, at time 0 I have 3/2 and 1/2 here, so that starts at 2, say, so 2, and it should be something like this. Both of them. This one starts at 2, and so both of them start at 2. As t gets larger and larger, this one gets small, very small. This one gets large, very large, right? That's e to power something. So this will be, say, at point 2, this is e to power minus 2. That's a very small number, right? And this is e to power 6. So this one dominates, and you will get, basically you get something which is similar to e to power 3t. Okay. So then both x and y with respect to time look like that. So with respect to time, they look like this. So then we write y with respect to time. That starts at 2 and looks like this. But if I consider them as x and y coordinates of a curve, then remember the parametric equations were introduced in the context of motion of a particle, which means we wrote down equation of motion, or let's say x and y coordinates of a particle moving in plane in that form as functions of time, some function of time. Now in this case these two. And then this gives me the path or the trajectory of that particle. So if I graph this thing, it's the path that the particle is taking and moving in that path. So if I start at another point, it gives me another path, right? So if I start at, say, 3 and 1, say maybe 3 and 1, I will get something else. It will be like this. So depending on where I start, or the particle starts, I will get something different, a different motion. And if I graph many of them for different points in plane, I will get something which gives me the feeling of some, say, flow of something. So it gives me a feeling of something is flowing. So it will be something like this. I know what it looks like. It will be something like this. Like this. So this gives a person a feeling of flow. So it's like some fluid is flowing and flowing this way and this way and this way and so on. And when you graph it, no, this, how do you graph this thing on Mathematica? It is in fact, it's called a stream plot. You can use stream plot. I guess if you stream plot on Wolfram Alpha, you should understand that's mathematical. So if you say there's just stream plot this thing for me, then inside this you give xt and yt and braces, and then say, okay, I want t to go from 0 to 0.4. That will give you a picture like this. And this picture is, it is apparent. If you look at it carefully, you will see that it's like there are two asymptotes here. What is an asymptote? You might have heard this asymptote in about that COVID-19. They say some people are asymptotic. I don't know if they know, but I guess that really means what it means. So they're using it correctly. Asymptote means that you get close to some threshold or some dangerous place or dangerous, say, zone, but you don't touch it. So which makes sense, because asymptotic means you get the virus, but you don't show too much say symptoms. So it's like this: you're getting close to this, and you don't touch it. So you really don't get that sick, but a little bit. So, and depending if you're here, it's asymptotic, but it's way up there. So you reach it way up there. Now, what are these two asymptotes? Let's see. This, when I started here, it was t equal to 0, and then t goes to 0.4. So it seems that as t gets larger and larger, they go this way. So let's see when t gets larger and larger and larger, what happens to the solutions. So let me write the general solution. X was c1 e to power negative t plus c2 e to power 3t, and y was minus 2 c1 minus t plus 2 c2 e to power 3t. Okay? So that was the general solution. I just found one of them. And okay, so what happens as t goes to infinity? Plus infinity. So let's analyze this as t goes to infinity, and let me erase these things, and you just keep this one here. And just look at this. Let me get this to it. So what happens as t goes to plus infinity? Well, e to power minus infinity is 0. And this is infinite. Okay, but it is not 0. So as this happens, x becomes almost c2 e to power 3t, right? Because this one really will not affect. And the y becomes almost this second one, 2c2 e to power 3t, right? Okay. So if this happens, I can say that y over x is basically 2, right? So that's y equals 2x. Now, what is this? What this y equals 2x? In fact, that is the direction. What is the direction of this? That's a line. The direction of this line is, in fact, the eigenvector, right? This is 1, this is 2. Remember, the eigenvector was for 3, eigenvector was 1, 2. Okay? So if I have 1 here, 2 here, then this is the direction of that line. So that this direction, in fact, the direction is this direction vector, and is in fact v2. 1, 2. So this line is in the direction of 1, 2, the vector 1, 2. The equation is y equals 2x, and it goes through point 0. And what happens when it goes to negative infinity? So that is positive infinity. What happens as t goes to negative infinity? Negative infinity, this one becomes 0. E to power 3t, that's minus something big, that's 0. But this one stays. So in this case, x will be almost c1 e to power minus t, and y almost minus 2 c2 e to power minus t. So in this case, y over x will be negative 2, and y is negative 2x. And that's this line. And this line, as you see, it is in the direction of v2, v1. 1, negative 2. You can see that. That's in the direction of y, 1, negative 2. So these two asymptotes are lines that go through point 0, 0 and are in the direction of the two eigenvectors. Eigenvectors 1, 2 and 1, negative 2. Okay, so when you draw the picture, and if you have lambda 1 and lambda 2, if the two are one is positive and the other one is negative, so they have different signs, and then this happens. But we will discuss this in other lectures. Because if both of them are negative, something else happens, and if they are positive, another thing. So, but in this situation, this is what happens. This is what happens, and the solution looks like this. And what happens to this as t goes to infinity? You can see that both x and y go to infinity. So the two solutions basically get larger and larger and larger. Like boom, 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 goes up. So if that represents some kind of, say, some device, I mean, so some system, say, the system is like breaking down, it's like dying. So we will see that this situation and the situation like this, we will discuss stability of stability in the coming lectures. So anyway. Okay, what else? What else can we learn? How did we get this thing? How did we get this guy here? These two. We solved this equation. X prime is x plus y, and y prime is 4x plus y. What is x prime, y prime? X prime, y prime is this guy here is velocity in direction x. This one is velocity in direction y, right? That's dx dt, dy dt. And so these two give me the velocity vector. So the velocity vector for, in this situation, in this case, is this. This thing. So the velocity vector for this particle, or some C1, C2 say, and it doesn't depend on C1, C2. So that is the velocity vector, which is the velocity in direction x and velocity in direction y, is in fact x prime and y prime, and it is this, x plus y, or x plus y. So it's interesting, the velocity vector is given in terms of position of the particle. Velocity vector given as position of the particle, this is some kind of function which takes points x and y and gives me x prime, y prime, which is like two points. So this is what we call a vector field. Remember, if you took Cat 3, you have seen vector field. In this situation, this vector field is like a function from R2 into R2. So what is the domain? The domain is in fact x and y, and this is taken to this vector, x plus y, comma, or x plus y. Okay? So mathematically speaking, this is in fact like equations for a vector field. What is that vector field? If I graph that vector field, that is the velocity field. That's why it's called velocity field. Sometimes the phase plane or something like that. But anyway, we have the velocity field. And velocity is what? Velocity is tangent to trajectory. So we know from Cat 3 that, say at this point, so this point has some x and y, say, let's say this is like 3, and let's say that this is 1. So if this is 3 and 1, this point is 3 and 1, say, then the velocity, which is like this, the velocity vector will be 4, 3 plus 1 is 4, 4 times 3 is 12, plus 1 is 13. Okay? So the velocity vector for this point 3 and 1, for the point 3 and 1, we have this velocity vector. And that's tangent to the trajectory. So if I graph this thing, how do I graph vector fields? That's what I do. That's what the mathematical does. So it just takes this point, finds this vector and then draws a vector at this point with these coordinates, with these two coordinates. So as I get further and further, the velocity vector gets larger and larger. So if you graph it like this, the velocity vectors close to zero are very small. Very small vectors, then it gets large. So it means that as you get further and further, it's just going crazy. So the velocity somewhere here is like 10,000, and that's like more than the velocity of the speed of light. So that's what I said. Even technically speaking, this is not stable. Even the velocity gets too large. So that is the velocity vector. So in fact, the problem, if we look at it as the motion of a particle, has given me a velocity vector. So the problem, the system of equations is in fact like this. It's saying that, okay, I give you a velocity vector in terms of position, velocity vector in terms of position, give me equation of motion. So velocity vector in terms of position are given to you, and you have to find equations of motion in terms of time. Okay? So physically speaking, this system of equations means something like this. So you can interpret that in this way. Given the velocity vector, find x and y as functions of time. That is the motion as the motion of the particle as a function of time. Okay? So, we had something like this. Remember, in fact, the very first problems that we solved, the simplest problems that we solved was like that. We had something like dy dt is some constant times y. Remember that we solved this thing. This is like velocity, this is the position, right? So that's velocity given velocity in terms of position, and this is for one-dimensional motion, right? That's for one-dimensional motion. It's just y, one dimension. So this is given velocity in terms of position, then solve it. And remember, we solved it, that's like e to power something. So this is like more general than that. It's given in terms of both x and y. That's why these two equations are, how should I say that? They go together. So I don't have x prime equals x and y prime equals y. No. That's not like a system, so you can solve them separately. Okay, so what we did was in fact this. Given velocity vector as function of position, find equations of motion as functions of time. Okay, and we have found them. These are like different trajectories that a particle with this velocity field can take. Now, depending on where it starts, you will get different trajectory. And this velocity field, if you use vector plot in Mathematica, if you use vector plot, in fact, and do the same thing as I did for stream plot, x plus y, and for x plus y, and y goes from 0 to 0.4. Anyway, you can just change that. Change it to something, whatever. Cool. And you can see it will give you something like this, except that you have, and these two lines, you can see these two lines, not easy to see, and then you will see like vectors like this, which are in fact and so on. So you will see vectors in fact, but as you get closer to 0, you don't see anything. If you go too far, you don't see anything because vectors here are so large and vectors here are so small. So basically, as you get closer to 0, it doesn't show you the vectors closer to 0 unless you divide this by its magnitude. Unless you divide this by its magnitude. If you remember, if you divide this vector by its magnitude, you make it unit vector. So if you do that, all of the vectors in velocity field have a length 1, except for this 0.00, which is not defined. So if you divide this by its level, what's the magnitude? The magnitude is this, x plus y squared plus 4x plus y squared. So if you multiply this thing by 1 over this magnitude, is multiplied, and graph it, then you will see them. All of them will be unit vectors. So this is good to see just the direction, not the magnitude. If you just graph it, it also shows you that the magnitude is small. As you get further and further, it is so big, very big. You don't see anything here. Just looks like a point compared to the other ones. Okay, anyway, so that is that vector plot will give you the velocity field, and string plot will give you trajectories. So try these things on Wolfram Alpha and see if it does that for you. And what else? Yeah, there is something else which this also tells me. These two equations. Let me give you that, and well, let me erase this thing. And so what happens if I set x prime equal to 0, that gives me x plus y equal to 0, that gives me y equals negative x. And if I set y prime equal to 0, then for x plus y equals 0, and that gives me y equals minus 1x. Well, let's see, these two lines, in fact, y equals minus x is this, and minus 4x is this. So, yeah, that's okay. It's like this, like minus 1, minus 1. So it's like this. So this is y equals negative x, y equals minus 4x. Now what happens? What is this one? This one is telling me that on this line, y equals negative x, x prime is 0. X prime is 0, which means that just we have y prime. So on this line, when the curve, the trajectory hits this line at some point, it hits this like this. So the trajectory looks like this here, or this way, it depends on which way it's going. What about this one? That is when y prime is 0. Sorry, let me see which one, that is x prime, yeah, that's correct. So that is when y prime is 0. Oh. Well, okay, so this one is y prime is 0, so the trajectories go like this. On this one. Because there is no y prime, so it's like it's hitting this horizontally, and this one they're hitting it vertically. Okay, so this is also another check and see if your trajectories are correct. So those two are like asymptotes. These are not asymptotes. These are the trajectories hit these two, and when they hit these two, on this one, x prime is 0, so you just have y prime, which means there is no x direction, so it's just y direction, so it goes horizontal. On this one, y equals negative 4x, they are y prime is 0, so it is basically in the direction of x prime, or x, say. So this is another thing you can see in the graph, in the stream plot. If you graph these two together with the stream, you will see this. If you graph those two, you can see, you can just look at it and you see when the streams intersect one of them, you see that it's like this or like this. Okay, so I have posted a long time ago, I posted lots of things on D2L for you. There are many examples on D2L regarding these things, and I have given So next time I will discuss the other situation, which is having two complex eigenvalues. Okay, so see you next time.